have decided not to talk about closure in this meeting because the word has been so much, caused so much confusion last time. However, Marina has put me to give a second talk on this, so it's therefore not mine. Our idea is to look carefully at crack closure, and particularly is the validity of assuming Elber's idea that fatigue crack driving force is delta K effective. That for me is a very important point. It's a very old discussion, never settled, because we still are using this idea in mechanical design. For example, coming from Brazil to France, I entered in a Boeing 777 that I'm sure has been designed assuming delta K effective as a fatigue crack driving force. They still use humans programmed to do that. So, as far as I am concerned, I am very, very, very much worried about that. The key question is, can delta K effective be used to explain to model all characteristics of fatigue crack growth behavior? In my opinion, it cannot. I do recognize that crack closure is a very reasonable and realistic explanation for many fatigue crack growth behaviors, but it has some limitations that simply should not and cannot be ignored in practice. All questions about the use of delta K effective, in my humble opinion, have to be supported by decent, proper opening load measurements. So I'm going to show you some simple data that simply cannot be explained by Elber's idea. We all know that fatigue growths are very much susceptible to sudden changes in crack driving forces, may cause sequence or load order effects. Several mechanisms can induce such effects. Fatigue crack closure is one of them. Fatigue crack closure acts before the crack tip, but blunting, kinking, bifurcation of the crack tip can delay crack growth as well. Mechanisms that act at the crack tip, and the residual stress and strains ahead of the crack tip can delay fatigue crack growth as well. And the importance of those mechanisms may depend on many factors. The size of the crack and of the residual ligament. Let's imagine for a while. Can we believe that opening load is independent of the size of the residual ligament? If the residual ligament is smaller, there's not much material to close the crack. Can we believe that crack closure is independent of the residual ligament? Transversal constraints around the crack tip. Residual stress around the crack tip. The load on the overload range maxima, the microstructure of the material, number of overload cycles, the environment. All of them can affect the fatigue crack growth behavior. And in many cases, one of the mechanisms is so dominant that others may become negligible, but in other cases they are not. Such mechanisms can interact and affect the fatigue crack growth behavior. They can interact competitively. For example, crack tip bifurcation after an overload can reduce the opening load and thus decrease the subsequent influence of crack closure. Or else they can act symbiotically. Martensitic transformation induced by plasticity increases material volume inside the plastic zones and tend to increase both residual stress ahead as well as practical opening load behind the crack tip. There are so many variables that can affect the fatigue crack growth behavior and variable amplitude loads that's really no surprise to still find a lot of controversy in this subject. To believe that overcrack closure is the single, at least the dominant cause for all sequence effects on fatigue crack growth may be questionable. In fact, there are some experts that simply affirm that plasticity-induced crack closure is irrelevant for fatigue crack growth. I don't believe it is. In some cases it may be important, in some cases it is not. There are a lot of interesting data to support both points of view. What I'm going to present here is some very simple closure measurements done in the way Elber himself proposed to do compliance measurements in order to identify the opening load. I had presented that in Urbino and made some conclusions on the measures made exactly as Elber made them a long time ago. Since the arguments I present question the use of delta K effective, some colleagues claimed the measurements were wrong. So in this meeting, I'm going to present still other completely independent measurements to support my conclusions. There are a lot of issues with delta K effective as the fatigue driving force. This hypothesis is a hypothesis made by Elber. In my point of view, has a huge problem. As a mechanical designer, I do not know how to calculate the opening loads for all specimen or component geometries. I can calculate the stress intensity factor, but I cannot calculate the opening loads. So from my point of view, the use of delta K effective as a mechanical designer is a major problem, because I have to assume some simplifications in order to calculate the opening load. I will not discuss all the details about questions. I'm just going to present one experiment that questions one point of the Elber's idea. The main point about Elber's idea is the crack tip can only be loaded after completely opened. That means if a point in the crack front is still closed, the crack supposedly would not propagate. So we decided to make a very simple test. We start the crack in mode 1 in an eccentric single-edge notch specimen. And the crack started to propagate as usual in mode 1 with a more or less straight front. Then we took the specimen, turned it, and started to load the specimen in bending. So part of the crack front would be closed by the bending loads, by the compressive bending loads. And the question was, oh yeah, if you have compressive bending loads, you are going to close, and I'm going to prove this to you. So the idea was, after bending the plate, part of the crack front will be closed, and the part will be open by the loading itself. What is going to happen with the crack front? The crack front, oops, it's below here, near straight cut front. After bending, the crack fronts become an L-shaped front. That makes sense? In my opinion, yes. What is the actual crack driving force? It's a global parameter, or is it a local parameter? If you have a positive driving force in part of the crack front, is not enough to make that part grow. In this particular experiment, this part of the crack remained still, and the crack started to grow, of course, the neutral line in the plate changes as the crack grows, and then the crack grows a little bit and above in the upper part as well. No doubt, part of the crack front is closed. No doubt the open part can propagate. So there is no way I can claim if I pick one point of the crack front, it is not going to grow. However, we decided to do an even simpler test in order to verify if delta K effective was indeed the fatigue tract driving force. Our idea was take thin and thick specimens from a round bar, a 3-inch round bar. Thin ones designed to have fatigue tract propagation driven under plane stress using classical definition of plane stress. Thick ones designed to have fatigue tract propagation driven primarily under plane strain conditions using, once again, classical definitions. Measure the opening load using compliance measurements. Strain gauge mounted in the back face of the specimen. A lot of strain gauge is mounted ahead of the crack tip to make close field measurements and far field measurements of the compliance. That we presented in Urbino. And the results we got were quite interesting. We grew the crack under fixed delta K conditions, using the very same procedure proposed in the ASTM E647 standard. Delta K defined in the correct way, or in the traditional way, using the maximum load and the minimum load. So R equals 0.1, delta K equal 20 megapascals per root of meters, almost constant DADN ratios when the crack grows from a very small size up to a large one. At the same time, we did measure the opening load. And the opening load started quite high and decreased as the crack grew. Maintained delta K constant. However, a huge increase in the opening load. Opening load started almost 70% of the maximum load, ended at about 0.4, 0.3 something. So the delta K effective has changed a lot during the propagation of the crack. However, the fatigue crack loss rates remained constant. This was for the thin specimens where the cracks were propagated under plane stress conditions. We should have different behavior on plane strain. At least is what we can believe if you believe in Elber's idea. So we took the 30 millimeter thick specimen and did the same test. Exactly the same idea. Delta K still 20, R is still 0.1. The ADN almost constant within the dispersion of the data. However, delta K effective varying a lot. Large value of opening load when the residual ligament was larger, smaller value when the residual ligament was smaller. This result, of course, is contradictory with Elber's idea. So it must be wrong, because Elber cannot be contradictory. That was the conclusion from Urbino. So I decided to do still another test. This time using digital image correlation to measure the opening load. More, I decided to ask a friend of mine, an expert in such measurements, and a truly believer in Elber's idea to do the measurements, just to avoid any bias whatsoever. So I asked him, train the students to do the measurements using whatever you want, and we did so. We did use a digital image correlation system. The specimen, the specimen is here. Here are the cameras from the digital image correlation system, illumination system, and we still use it, the back face strain and the strain gauges in the line of crack growth. So we made at the same time 4 different measurements. compliance measurements in the far field, compliance measurements in the near field, digital image correlation measuring the opening of the crack tip. Professor,
without professor.
Yes, yes, showing exactly the same technique we used in this field. We did the very same exercises in order to calibrate the system, whatever. And we also used the strain field ahead of the crack tip to measure the opening noise. Using this kind of information. We did avoid, though, the very near part around the crack tip to avoid the plasticity constraints. Just to use the Williams field and things like that with confidence. Those are the results we got. 4 types of measurements. Measurements based strain gauge in back face, strain gauge near the crack tip, DIC near the crack tip, and COD using the DIC. Look, the opening load we measured by 4 completely independent systems within the dispersion of the experimental techniques. Oops. Very same thing using thick specimens, and once again we got the results plotted in the way we did before. Crack propagation rate under constant delta K, almost constant. However, a huge variation of the opening load measured along the crack path. There is no way I can claim this particular test was driven by delta K effective. Thick specimens, the specimens were different, the results are not identical, they have not been treated to fit anything, the dispersion is there. We decided to make still another test changing the value of delta K, now 15 megapascals per root of meters, very same trend. Thick specimens, thin specimens, this was not as thick as the other one because we had increased the maximum stress intensity factor, so to maintain plane strain conditions. We could use less thick specimens. The bar was ending, so we don't have too much material to continue the tests. Conclusions. Very simple and easy reproducible data. It confirms, thanks God, that we can use delta K as a similitude parameter in fatigue glucose predictions. I can correlate the ADN with delta K. Very happy with that because I know how to calculate delta K. It also confirms the classic view that fatigue glucose rates measured under fixed R ratios can properly characterize the fatigue glucose behavior of this material independent of the specimen thickness. It also questions the alternative view that delta K effective is the actual crack driving force. Those experimental procedures are the simplest test I can imagine to verify Eller's idea. And they can be easily reproducible in any laboratory. So, the only thing I can say here to avoid the huge discussions we had in Ubino is try by yourself. I don't know how to do better. I have used 4 independent measurements of the open load. The only thing I have not made yet is to use tomography to see how the crack opens along the crack. I'm going to do the next, but I have to use an aluminum alloy because my tomography is not powerful enough to work with steel. Hopefully, in the next meeting, it will be in... Oh, that will be great. Nobody will care about my results. I will be able to present still another way of measuring the opening load using tomography in the aluminum alloy. Well, that's what I have to say. Anyway,